Okay, here we have a classic sort of question from a calculus exam asking about a rational function and its graph and properties. So first we want to find the vertical asymptotes. Well, what causes vertical asymptotes is division by zero. So we have to figure out where is this denominator equal to zero. So we need to factor the denominator. Well, I can see that's going to factor as x minus 3 and x plus 2. So it's tempting to say right away that the vertical asymptotes occur at x equals 3 and x equals negative 2. But I've missed something. You have to factor the numerator as well and see if it has any of the same factors. The numerator is x plus 2 and x minus 2. So because this x plus 2 also appears in the numerator, it's not going to be a vertical asymptote. It's going to be a hole instead. So it's just going to be one single spot in the graph that's missing instead of a whole vertical asymptote. So that's not a vertical asymptote. Only x minus 3 is a vertical asymptote. Okay, so then how do you find the horizontal asymptote? You have to take the limit as x approaches infinity. Now for a function like this, taking the limit as x goes to infinity is the same as just doing it for the leading terms. So we can literally completely disregard all the other terms except for those two. And I think you'll agree that that's pretty easy because x squared divided by x squared is just 1. And then the limit as something goes to infinity of just 1 is just going to be 1. So that means the horizontal asymptote is going to be y equals 1. Part B asks, when is this function discontinuous? Well, the only thing that causes a discontinuity in a rational function is the division by 0, and we already figured out that the denominator is going to be 0 when x is equal to 3 and when x is equal to negative 2. Now this one is a vertical asymptote because it's got a factor of x minus 3 on the bottom and not on top. But negative 2, right, the factor of x plus 2 is on the bottom and on top. So that's not going to be a vertical asymptote. That's just going to be a hole. Some people don't like to call it a hole for some reason. It can also be called a removable discontinuity, like that. So yeah. Okay, the limit as x approaches 3. So x approaches 3 is the vertical asymptote. And because it's got that factor of x minus 3 just once in the denominator, and then the other guys are x plus 2, x plus 2. If they ask for the limit as x approaches negative 2, that would be much more interesting. We would cancel this out, and then we would just plug negative 2 into here. But because they asked for the limit as x approaches 3, well, that's going to cause this denominator to be 0, and the numerator is not going to be 0, and so it's going to be just infinity. But is it going to be plus infinity or minus infinity? Well, it depends on which side we approach 3 from. If we approach 3 from the right, it's going to end up one way, and if we approach 3 from the left, it's going to end up the other way. Which is to say the graph is going to be one of these. It's going to be one of these sort of double-sided vertical asymptotes as opposed to one of these like that. And so since it's a two-sided thing, it's positive infinity on one side and negative infinity on the other side, that means the double-sided limit does not exist. Part D is asking us to take the derivative, so we can do that using the quotient rule. I like to remember it's low d high minus high d low over low squared. So that's low, and then d high is going to be 2x minus high d low, so that's high, and then d low is going to be 2x minus 1. Gosh, what a mess. And then over low squared. All this. Alright, you can simplify that if you want to, but fuck that. Okay, and finally we have the integral from 1 to 2. Now they warn us that it might not be possible. The reason that it wouldn't be possible is if that interval included that vertical asymptote. But it doesn't. We know the vertical asymptote is over at x equals 3, and 3 is not in between 1 and 2, so we don't have to worry about that. It should be possible to calculate this integral. Now, how do you actually do this integral? Well, we got to do the integral from 1 to 2 of this function. Now, as long as you don't include the value that's like the problem value, it's safe to just cancel those factors. So we could simplify this thing to x plus 2. Oh no, my bad. X minus 2 and x minus 3. Like that. Okay. Now I'd love to simplify that even more. It's too bad that the numerator is not x minus 3, right? Well, maybe it can be x minus 3, because isn't x minus 2 just x minus 3 plus 1? And then isn't that the same as splitting this up like this? I could just give it a x minus 3 over x minus 3 plus 1 over x minus 3, like that. Why do I want to do that? Because now that left term is just 1. Nice and easy, nice and easy. And now I can take the antiderivative of each piece. That is surely x. That is surely the natural log of absolute value x minus 3. Don't forget that absolute value. It's going to matter in this case. And then we're doing that from x equals 1 to x equals 2. And so then if we calculate that out, that's going to be 2 plus the natural log of 2 minus 3 minus, let me do that on the next line, minus 1 plus the natural log of 1 minus 3. Okay, now if we calculate each of those, that's going to be 2 plus the natural log of the absolute value of negative 1, which is the same thing as the natural log of 1, which is the same thing as 0, minus 1 plus the natural log of the absolute value of negative 2, which is the same thing as the natural log of 2, and that's some irrational value. So finally we end up with 2 minus 1 plus the natural log of 2, and we can only simplify that a little bit. It's going to be 1 minus the natural log of 2. So there you have it. Good luck on the exam.